Okay, hello, Mr. Heisinger here. Today we're going to start into Chapter 16, looking at electric force. There's a lot of Chapter 16 that we're not going to cover. I'm going to just hit the key ideas that's necessary to understand electrical power and energy that we'll cover in Chapter 17. So this is going to be somewhat brief. Let's go ahead and get going. First, just learning targets that we're going to look at for Chapter 16.1. Just a few pages to read, understand basic properties of charge, differentiate between conductors and insulators, and then we'll need to do some calculations on how to determine number of charges that are transferred, and these will be a couple of problems that we'll have you do. Okay, just properties of electric charge. From atomic theory, you should know what each one of these subatomic particles are called, and so this is a picture of an atomic nucleus. We've got some of these positive charges in the nucleus. We've got some of these orange objects here that don't seem to carry a charge, and then we have these things that are floating around the atom, if you will. And you probably remember what these things are called. In case you don't, what we see here is that the positive charges in the middle are called the protons. The neutrons are these things in the middle of the nucleus that have no charge, and then the electrons are sort of hovering around the outside of the nucleus, and they carry a negative charge. So make sure you know the names of those things and what the proper charges are for those. Now we should also know some things about electric charge. When the woman rubs that balloon against her hair, you see that the hair starts to attract to the balloon, but yet these balloons sort of repel, and the reason for that is that opposite charges attract and like charges repel. And again, this should be a review for you from some of your earlier grades. So you can see that there were positive charges on the hair and negative charges on the balloon, and that caused them to attract. And over here they repel. Now what does it mean when we say that an object is charged? Simply, that just means that there is a inequality between the number of positive charges and the number of negative charges. So when we say something is charged, that just means that there's more of one type of charge than the other. So in this particular example, if we lose a couple of electrons to go off to go somewhere else, then this will carry a positive charge, since we now have more positives than negatives. Now when we do work on an object, we can cause it to heat up, such as when you rub your hands together, but it can also cause charges to be separated. So what else can work cause? If we take those balloons and we rub them against a sweater, what we see is that we can actually cause the charges to be separated. And so those balloons rubbed against that sweater will cause some of the charges to be removed from the sweater and be now affixed to the balloons. So we've actually separated charges with the work that we've done. Now there's another important idea about charge conservation. The number of charges transferred from the to the balloons from the sweaters is exactly the same. So what one loses, the other gains, and this is a fundamental idea behind charge. Just like mass, charge is a conserved quantity. What one loses, the other one gains. We cannot create or destroy charge. We simply transfer charge from one object to the other. Now which type of charge is transferred? Is it the positive charges or the negative? And this picture sort of shows that. It's the negative charges that are transferred, and again, the reason behind that is that the electrons are somewhat loosely held to the nucleus. Some of the electrons are easier to remove from others, and you may know that from your chemistry classes, but the protons are relatively fixed inside the nucleus. We're not going to really get those to be removed from the atom. They're going to be pretty much fixed in the nucleus, and the electrons will be what's transferred. Now, Robert Millikan did an oil drop experiment way back in the early 1900s, and what he revealed about charge is that charge is a quantized material, or quantized substance. Now that's sort of hard to understand what we mean by quantized, so let me try to explain that. That was his main outcome, is that charge is actually quantized, which means it has a specific quantity. The charge comes in set amounts that's equal to, each charge has a charge equal to 1.6 times 10 to the negative 19 coulombs. That's the charge on a single electron. It's quite ingenious really how he discovered this, but I would encourage you to follow some links and to look at the oil drop experiment through some videos, and you'll see what he actually did. But the idea behind the charge is quantized concept is that It's sort of like the penny. The penny is the smallest denomination of U.S. currency. Everything else is sort of made up of multiples of that penny. So the quarter is 25 pennies, the nickel is 5 pennies, the dollar is 100 pennies, and so forth. The pennies sort of serve as the equivalent to the electron in terms of how much charge an object can have. It's always whole number multiples of that smallest amount of charge. And that wasn't known until Millikan did his oil drop experiment. Now down here we have a table of different charges and masses for various things, the electron, the proton, and the neutron. Notice the neutron does not carry a charge, so its charge is 0. That means it can't be influenced by other things that have charge. Whereas the electron and proton have the same amount of charge, but one's negative and one's positive. Masses are very similar for the proton and neutron. They don't differ by that much, whereas the electron is quite a bit smaller in mass than the other two. Now we also have to be able to do some calculations with things. Let's say that we rub a balloon against your hair, and that results in a transfer of charge equal to 1.2 microcoulombs. How many electrons were transferred? Now we should make a note here that 1 coulomb of charge, in order for us to have 1 coulomb, we need to have 6.2 times 10 to the 18th electrons. And that idea is that since 1 electron has a charge of 1.6 times 10 to the 19th coulombs, 10 to the negative 19 coulombs, I'd actually need to have this many electrons in order for that to be equal to 1 coulomb charge. So it's really just saying I need that many of these charges to equal 1 coulomb. So that number becomes important. A coulomb of charge is a large number of electrons, and we'll use that coulomb idea a lot in chapter 16 and 17. So let's figure out how many electrons have been transferred if we transfer 1.2 microcoulombs. So first thing we want to do is we want to take care of the prefix. 1.2 microcoulombs is the same as 1.2 times 10 to the negative 6 coulombs. So micro means negative 6. And so that's just a shorthand way of writing this in scientific notation. Now next I want to do a little conversion. So what I'm going to do is I'm going to take 1.2 times 10 to the negative 6 and multiply it by this conversion factor. These are equivalent amounts of things. I need 6.2 times 10 to the 18th electrons to be for 1 coulomb of charge. So when I multiply these two quantities together, what I see is that the coulombs reduce and I get a number of electrons that would be transferred. And that number is about 7.4 times 10 to the 12th. So a very large number of electrons transferred during that rubbing process. And so she does work on that balloon, and by doing that work, she transfers some electrons to it. Now if we take a look at copper, this is a copper fitting that plumbers might use to be able to run some water lines in a home. 1 cubic centimeter of copper has about 6.2 times 10 to the 23rd free electrons. Now when I say free electrons, I mean those are the electrons that are somewhat easy to be removed from the copper atoms. And so they can easily transport things like electricity, stuff like that. So let's go ahead and take a look at how we would do that conversion. 6.2 times 10 to the 23rd electrons. And in 1 coulomb, I have 6.2 times 10 to the 18th electrons. So what I'm going to do is just multiply these two quantities together. And you notice the electrons reduce and I get coulombs left over. And what that is about 100,000 coulombs of charge. Now notice the conversion factor that I'm using is really the same conversion factor. It's just flipped around. Whether or not I put the electrons on top or the electrons on bottom all depends on whether or not I'm converting from electrons to coulombs or from coulombs to electrons. So be familiar with this conversion factor and just be able to use that to convert from one kind of thing to another. Now down here I have a data table that I wanted you to that I want you to try. And what I'd like you to do is I'd like you to pause the video and try to fill in these different rows in these columns to try to see if you actually understand how to use this conversion factor. So go ahead and pause the video and give that a shot. Okay, so now hopefully you've had a chance to try that. What you should see for this one is that the net charge, if I have that many extra electrons, is that you have about negative 5.2 times 10 to the negative 7 coulombs of charge. And this would be the conversion factor that you would use, the way you would write it. Now you could either write that as 10 to the negative 7, or you could go 0.52 microcoulombs or 520 nanocoulombs. And again, that negative's there because these are electrons, and so that would have a negative charge. Now for this one down here, the conversion factor that I would use would be 6.2 times 10 to the 18th protons per coulomb. And so when I do that, I see that the number of protons transferred in this particular, I wouldn't transfer the protons. What I would do is I would transfer the electrons away and have this many extra protons that remain. So that'd be 2.32 times 10 to the 10th. And again, that's just multiplying these two together. And this last one's a little bit tricky. In order for me to determine the net charge, I have to subtract these two. In this case, I have more electrons than protons. When I subtract those, I see that I have 7.27 times 10 to the 21st extra electrons. When I go through and convert from those electrons into coulombs, what I see is that that would be the conversion factor. That would be about 1172 coulombs. So we would say it's got a negative 1172 coulombs of charge. And last slide for us is that when you talk about classification of materials, we're going to look at the classification based on mobility of charges, whether or not the charges are free to move. So metals are usually have charges that are free to move about, so the electrons are loosely held. We would call those conductors. And insulators would be the charges are somewhat fixed in place, so things like plastic, rubber, glass, silk, and so forth are insulators. Typical household wiring, the conductors are the substances, usually copper, that would carry the electrical charge for electricity throughout our home to power our devices. And then the insulators would be the things that protect the household or protect the person running these cables, protect them from the high voltage that would be in these cables. So insulators do not conduct charge. And then down here what we have are semiconductors. Now semiconductors are really useful because we can make the mobility, we can either turn the charges on or off, and so we can use these as somewhat of like a switch. So turn things on or off. A lot of times our semiconductors, we might use silicon as our main semiconductor, but silicon by itself is not a semiconductor. What we have to do is we have to do some doping on it, and doping just means that we add some impurities, and those impurities now give it some semiconductor properties. And what's not listed here and what's not talked about in your book is this thing called superconductors. Superconductors are really, really fascinating materials that actually conduct electricity without any loss of energy to resistance. And you may have heard of those before. That's just another breed of conductors. They're just called superconductors, so they don't offer any resistance at all. I'm going to stop there with section 16.1. There's only a few problems for you to try, and again I want to give you a chance to try those. These would be those problems, and then come to class with questions. I hope that helped. We'll see you tomorrow. Go Bucks.